So today we will discuss about chemical equilibrium. Okay, already we have talked about this, the first part. The continuity we will do in this video. I am Anthony Raj from CVetrii Neet Gateway. Right. So in the last class you discussed about the application of equilibrium constant, right, which can be used to find out the extent of the reaction. Okay. So how far the forward reaction and reverse reaction will happen depending upon the equilibrium constant value. So today we will study another application using reaction quotient. First, what is reaction quotient? Okay, let me take a simple equation: A times A, B times B, reversible gives C times C, D times D. Okay. So we discuss equilibrium constant. Okay. So Kc will be equal to constant of C equilibrium power C, constant of D equilibrium power D, constant of A power A, okay, B. So please note that, so here the concentrations are taken at the equilibrium state. Okay. Then it is equilibrium constant. So the same expression only we use for reaction quotient also. So Q will be again the same expression only. Okay. D power D, A power A, B power B. So same expression only, but these are non-equilibrium concentration. That is, before attaining equilibrium, okay, we calculate reaction quotient. Okay. So now by comparing the value of Q and Kc, okay, we can come to know the direction of the reaction. Where there are two reactions, one is a forward reaction, another reverse reaction. So we can know the direction of the reaction, right? So ultimately, the reaction is going to come to the equilibrium constant only. Okay, that is the final stage of the reaction. Okay, after that, the reaction will not proceed. That is the end of the equilibrium reaction, right? So therefore, by comparing Q and Kc, we can come to know the direction of the reaction. Okay, so we know that when Q is equal to K, the system has already attained equilibrium, right? When Q is equal to K, the reaction is already in equilibrium. Okay, if the Q is more than K, right? If the Q value is more than K, now Q value is more than K, now the direction is towards K only, because this is the ultimate state of the equilibrium reactions. Now from Q it has to reach K. That means Q is greater than K, so the value of Q has to come down, it has to reduce, right? Q value is more than K, so therefore to reach equilibrium, Q value has to reduce. How Q will reduce? If Q has to reduce, then the A and B concentration has to increase, or C and D concentration has to decrease. Okay. When will that happen? During the reverse reaction, right? Okay, during the reverse reaction only, AB concentration will increase and CD concentration will decrease. So therefore, so Q has to decrease to attain Kc, because now the Q is greater than K. Okay, therefore, the reverse reaction will be favored. Now the direction of the reaction is from right to left. Okay, similarly, if you take Q is less than K, if you calculate value Q which is less than K, now the Q value is less. Okay, ultimately it has attained Kc only. Now Q has to increase. When Q will increase? Only when the CD concentration increase or A and B decrease. That will happen in the forward direction. Okay, therefore, if the Q is less than K, the reaction will move towards in the forward direction, that is from left to right. Okay, so by calculating the Q value, okay, at different stages, okay, not necessarily at equilibrium, then we can find out at what direction the reaction will proceed, okay, thereafter. Okay, that can be calculated, that can be found out by calculating the value Q. We will take a problem and try to understand this. Okay, right. So we'll take an example. For a reaction 2A giving B plus C, Kc value is given. At a given time, the composition of the reaction is A, B, C are equal to 2 × 10⁻³ m. Predict the direction, right? So we have to find out Q, Kc is given, Q is equal to, okay, this is the reaction. For this reaction, Q will be equal to B concentration of C divided by concentration of A square, right? Okay. At a given time, the composition of the reaction mixture is, okay, so this is not at equilibrium, but at some time other than equilibrium. The reaction proceeds, it does not attain equilibrium yet, at some given time, we are taking, the value is given. So substitute this, all the three constants are equal only. So 2 into 10 power minus 3 into 2 into 10 power minus 3 divided by A square, which is 2 into 10 power minus 3 square. Okay. So we can see, so it gets cancelled. Okay, the value is equal to 1. Now Q value is 1. Okay, I am comparing this with Kc. Kc is 4 into 10 power minus 3, which is around 0.004. Okay, it is clear that the Q value is greater than Kc. Right? Q value is greater than Kc. Okay, so now Q has to reduce. That means the reaction will proceed in the reverse direction. Okay, right? Okay, so it will, reverse reaction is favored. Reverse reaction is favored. Okay. So Q value is more. Okay, to attain equilibrium, the Q value has reduced towards Kc. Therefore, the reverse reaction will be favored. So more A should be formed from B and C. Okay, so I believe you have understood this example. Right. So next we have to study about Gibbs energy change. Okay, what is the relation of Gibbs energy change with the equilibrium constant? Okay, so kindly note this equation, right? Okay, so delta G is equal to delta G naught into 2.303 RT log QC. Okay, so convert a log into ln. So delta G is equal to delta G naught plus RT ln Q. Okay, right? So to convert Q to ln Q to log Q, multiply by 2.303. So this is the equation, right? So when the system attains equilibrium, the delta G value will be equal to 0. At equilibrium, delta G is 0. Okay, so delta G is 0, right? And it has attained equilibrium, so QC will be equal to Kc. So therefore it becomes 0 is equal to delta G naught plus 2.303 RT log, instead of Q, write Kc. Okay. So therefore, if you bring delta G to the left, so delta G naught will be equal to minus 2.303 RT log Kc. Okay, this is the relationship between standard Gibbs energy change and Kc. Okay, so it's given minus 2.303 RT log Kc. Okay, as you know, for gases, we can also use the value Kp instead of Kc. So delta G naught will be equal to minus 2.303 RT log Kp. Okay, so right. So now I'll take that equation. You can also write like this. Okay, delta G naught is equal to minus RT ln Q, right? Okay, so or I can write minus delta G naught by RT is equal to ln K actually. Okay, so when we delta G is equal to 0, I can write as K. Okay, right. So ln K, right? So to the base E, therefore K is equal to e power minus delta G by RT. Okay. So K is equal to e power minus delta G by RT. We can also use this equation. We'll discuss about this in a short while. Okay, so like this we can derive. Right, so now we'll do a simple problem. The equilibrium concentration of the species in the reaction A plus B giving C plus D. A plus B reversible giving C plus D. Right, the values are given, right? So concentration of A is 2 mole per liter and concentration of B is 3 mole per liter. Concentration of C is given 10 mole per liter and concentration of D is 6 mole per liter. Right? The values are given. Okay, temperature is given 300 Kelvin. Okay, we have to find out delta G naught. R value is given calories. Okay, so the formula is delta G naught is equal to minus 2.303 RT log Kc. Okay, so this is the formula, right? So now first we'll find out Kc. Okay, this is the equation. A plus B gives C plus D. So Kc is equal to concentration of C, concentration of D. So these are equilibrium concentrations. A, B is equal to, okay, so C is 10 into 6 divided by 2 into 3. Okay, right. So if you cancel 5, 3, 2, so it is 10. Kc value is 10. Okay, now we'll substitute in the equation delta G naught is equal to minus 2.303, R is 2, the answer will be in calories, T 300 Kelvin, log Kc value is 10. You know log to the base 10 is 1, so it will be equal to minus 2.303 into 2 into 300. Log 10 is 1, so it is minus 600 into 2.303. You can multiply and find out. So many calories. So many calories per mole. Okay. So this is the final answer. Are you able to follow this? Okay. So the relationship between the standard Gibbs free energy, okay, and constant Kc, equilibrium constant based on concentration is this equation, right? We'll do another small problem. 2 moles of PCl5 are heated in a closed vessel of 2 liters. At equilibrium, 40% PCl5 dissociated into PCl3 and Cl2. Find out the equilibrium constant. Okay, right. Dissociation of PCl5. Right. So PCl5 is a gas. Reversible, it gives PCl3 gas plus Cl2 gas. Right? Okay. The volume is given, which is volume is 2 liters. Okay. At equilibrium, 40% PCl5 dissociated. Find the equilibrium constant. Right. So initially you take 2 moles, right? So we'll write initial. Okay. So PCl5, then PCl3, Cl2. Okay. So initially we have taken 2 moles of PCl5, PCl3 and Cl2 not present initially. At equilibrium, okay, 40% of PCl5 dissociated, so that is 2 minus 2 into 0.4, okay, right? So out of 2 moles, 40% dissociated. So 2 into 0.4 dissociated, okay. So from the equation, if 1 mole of PCl5 is dissociated, you get 1 mole of PCl3 and 1 mole of Cl2. That is the stoichiometry, right? Okay. So here 2 into 0.4 moles dissociated. Okay. Therefore, you get 0.8 moles of PCl3 and 0.8 moles of Cl2. Right? This is the equilibrium constant. Equilibrium number of moles. At equilibrium, moles. Number of moles at equilibrium. Right? So 2 minus 0.8, which will be equal to 1.2. Then, okay. If 1 mole of PCl3 dissociate, you get 1 mole of PCl3, 1 mole of Cl2. Therefore, get 0.8 moles of PCl3 and 0.8 moles of Cl2. But dissociated is 2 into 0.4. 40% dissociated. Right? So now, concentration. Concentration is number of moles divided by, okay, the volume, 2 liters by 2. 0.8 by 2. 0.8 by 2. So this is 0.6, okay. So this will be 0.4, again 0.4. So now we can calculate the equilibrium constant. Kc is equal to concentration of PCl3, concentration of Cl2 divided by concentration of PCl5, which is 0.4 into 0.4 divided by 0.6, okay, or it is 4 into 4 by 6 into 10, 2 times, 3 times, 2 times, okay, which will be, okay, 8 by 30, again 5, okay, right. So it will be equal to 4 by 15, right, okay, which will be equal to, okay, we can calculate and write the value, right, so 4 divided by 15, so which is 0. 0.215s are 30, 100, okay, 6, 90, then 100, no, around 2.66 you will get, okay. So that is the equilibrium constant for this problem, right. So we'll try to do one more problem. For the decomposition of the compound NH2 COO NH4 solid reversibly gives 2NH3 gas plus CO2 gas. Okay. Please note that the reactant is a solid, right? So the Kp value is given. Kp is 2.9 into 10 power minus 5 atm cube. If the reaction is started with 1 mole of the compound, what will be total pressure? Okay. So reactant NH2 COO NH4 NH3 CO2. So this is solid, gas. Okay, right. So initial, we take 1 mole of the compound. Okay, so these two will not be there, right? Let's say X moles dissociate, right? Okay, so at equilibrium, if X moles of reactant dissociates, stoichiometrically, look at this equation. Okay, stoichiometrically, we get 2x of ammonia and 1x of carbon dioxide, right? If X moles of reactant dissociate, stoichiometrically, we get 2 moles of ammonia and 1 mole of CO2, 2x, x. Okay, right. So now we have to find out, we are given Kp value. Okay, so you have to calculate the partial pressure. Kp value is given, find out the partial pressure. For that, you must know the mole fraction, right? So total number of moles now. Total moles. Okay. So please note that we should not add solid. Okay, because the solid does not exert any partial pressure, we have to leave this. So only these two gases will be, the moles have to be added to calculate the partial pressure. Total moles is 2x plus x, 3x. Okay. Now the partial pressure of NH3 is mole fraction of NH3, number of moles of NH3, 2x by total number of moles into total pressure, P. Okay, right. So it will be, x will get cancelled, you get 2P by 3. That is the partial pressure of NH3. Now partial pressure of CO2 is x divided by 3x into P. If you cancel, you get 1 by 3 P, right? This is partial pressure. Now you substitute in the Kp equation. What will be Kp? Kp will be equal to partial pressure of NH3 power 2. So we have a stoichiometric coefficient 2 here into partial pressure of CO2. Right, now we substitute the values. Okay, Kp is 2.9 into 10 power minus 5, right? Okay, that is equal to partial pressure of NH3 is 2P by 3 square. Partial pressure of CO2 is, okay, 1 by 3 P. Okay, it will become, so 4 by 9 P square into 1 by 3 P, that is equal to 2.9 into 10 power minus 5. Okay, so now the P, so if you rearrange, PQ will be equal to 9 3s are 27 into 2.9 into 10 power minus 5 divided by 4. If you calculate, you will get a value. You take cube root, you will get the total pressure. Okay. So are you able to follow this? Okay. So when Kp is given, you are supposed to find out the partial pressure. To know the partial pressure, you must know total number of moles at the equilibrium. Okay. So first we calculate total number of moles equilibrium. Only gases, solid has to be left. Then mole fraction into total pressure will be partial pressure. Then substitute in the equation accordingly. Okay. Then equate that to Kp, you will get total pressure. So in an equilibrium system, right? So even if the concentration of reactants are doubled, okay, the equilibrium constant remains the same. Okay. If the concentrations are doubled, then more products will be formed and the products will give back to the reaction and it will reach equilibrium. Again reach equilibrium, but the equilibrium constant remains the same. Okay. Right. So on doubling pressure and volume also, the equilibrium constant will not change. Right. But equilibrium constant changes only with the change in temperature. Okay. Right. Right. So we have seen this equation already. Okay. So I already explained this. Delta G naught is equal to minus RT ln K. Right. So then so ln K will be equal to minus delta G naught by RT. Or K will be equal to e power minus delta G naught by RT. So we already derived this equation, right? Now we'll see this closely. In this equation, if delta G is less than 0, that means the delta G naught is negative, right? If delta G naught is negative, then the overall term becomes positive because minus of minus will become positive. Okay, so the overall term becomes positive. That means e power a positive value, the K will be more than 1. Right? That implies that, okay, the reaction is proceeding in the forward direction. The reaction is proceeding in the forward direction. Because K is greater than 1, that means the products are more than the reactants. The products are more than the reactants. Okay, the reaction is proceeding in the forward direction. Similarly, we can also see that if delta G naught is positive, then the overall term will be negative. So it will be e power minus some value. Okay, then the K value will be less than 1, right? Which implies that the reaction in the forward direction is very less only. If K is less, then less products are formed compared to the reactants. Okay, that's what K less than 1 means. The products are much less than the reactants. Okay, so therefore, if delta is negative, then it is proceeding in the forward direction, more products are formed. If delta is positive, then the reaction proceeds only in the forward direction only to a small degree, right? So the last part of this lesson is Lee-Chartier's principle, right? Okay. So the principle says, in the equilibrium system, the conditions are very important. The conditions can be pressure, the concentrations, okay, then the volume, temperature. So these are very important. Okay, a system is at equilibrium. Now we are disturbing this equilibrium by changing any one of these conditions, right? What will happen? The system will change in such a way that, okay, the system will react in such a way that the disturbances are reduced, okay, or counteracted. That is how the system will change. Okay, we will try to discuss this in detail. Okay, we'll take some examples and discuss. Okay, the principle is the system is at equilibrium. Okay, we are creating a disturbance by changing pressure, volume, temperature, concentration, etc. Now the reaction will adjust or react in such a way that the disturbances get nullified or counteracted. Okay, we'll take some examples and explain. Effect of change in concentration. Okay, we'll take the example of the manufacturing of ammonia. So N2 gas plus 3H2 gas reversible giving 2NH3 gas. So very important reaction in industrial applications because ammonia is used in the production of fertilizers like urea, diammonium phosphate. Okay, so much of ammonia is produced, but the reaction is an equilibrium reaction, right? Okay, if you increase the concentration of reactant, say N and H2, right? Now I have increased the concentration, so I am disturbing the equilibrium. Therefore, the system will react in such a way that it will form more products, right? Okay, and the equilibrium will shift to, okay, another equilibrium state. Okay, the addition of reactants will not just remain there. The reactants will get consumed and will form more products. Then those products will form reactants again and it reaches another equilibrium state. Okay, so here an important point is, generally in any reaction we are more interested in the yield. Okay, we take some amount of reactants, okay, how much yield we get, that is for a particular amount of reactants, how much is converted into product, that is what we call as yield. Okay, so to get better yield, so what you have to do, right? If you want to get better yield of ammonia, what do we do? If you keep liquefying ammonia, that is by reducing the concentration of the product. Okay, so if you keep liquefying ammonia and keep removing ammonia from the system, that means that I'm reducing the concentration of the product. Okay, so Kc is NS3 power 2 by N2 H2 power 3. Okay, right? So if you look at this equation, okay, by increasing the concentration of reactant, that is by increasing the denominator or by removing the product, like you can liquefy ammonia and keep removing it, in both ways we are trying to reduce the value of Kc, right? We are disturbing the value and the value gets reduced. Okay, so now what happens? So in order to get back to Kc, okay, more ammonia will be formed or more reactants will react, give more products so that we get back this Kc. Okay, it will always try to maintain equilibrium. Okay, whatever conditions you change, okay, it will try to attain equilibrium. Okay, that is what is explained by Lee-Chartley's principle. Similarly, the production of calcium oxide. So calcium carbonate solid giving calcium oxide solid plus carbon dioxide. So look at this equation. So in this equation, it's the equilibrium equation we use to produce calcium oxide. Now there is only one gas. What I can do, if you keep removing the CO2 gas continuously, okay, in order to replenish the product, the reaction will proceed in the forward direction. Okay, the purpose of any reaction is to get good yield of the products. Okay, so by increasing the concentration of reactants or by continuously removing the products, okay, we can shift the equilibrium towards the forward direction. Okay, that is how the system will react. Okay, it will adjust itself. Therefore, in both the cases, by liquefying ammonia, by removing the product or by removing carbon dioxide, I can shift the equilibrium towards the forward direction. Okay, so this is how the concentration change will affect the equilibrium, and that is how the system will react. Okay, right. Now, effect of change in pressure. Okay, so now the second condition is changing in pressure. We can take the same example, like the manufacturing of ammonia, right? N2, okay, gas plus 3H2 gas giving 2NS3 gas. Okay, now I am changing the pressure. Let's say we're increasing the pressure. Okay, if you increase the pressure, you can clearly see the reactant has 4 moles of gases. The product gas 2 moles of gases. Now if I increase the pressure, okay, the volume will naturally get reduced. It has to get reduced, right? If you increase the pressure, the volume will be reduced in a gaseous system. So therefore, if the volume has to get reduced, then the equation has to move towards the forward direction, right? Because the reactants have only 4 moles, products have only 2 moles. Therefore, here the change in pressure will affect the reaction to proceed towards the products. The forward reaction will be favored. Similarly, if you reduce the pressure, then the volume has to increase, then the reverse reaction is favored, okay, according to Lee-Chartley's principle. Okay, so therefore, the equilibrium is a dynamic system. By changing the conditions, the system will adjust in such a way that, okay, the effects are reduced or counteracted. Okay, right? So that is how the system will change, right? Okay, so this is about the pressure. Similarly, if you increase the volume, okay, where the volume is increased, okay, that side will be favored. The volume is reduced, then in which direction the volume is reduced, okay, that direction will be favored. Right. So next one is effect of change in temperature. Very, very important. Okay, right. So we will consider maybe the same equation, N2 plus 3, N2 gas, N2 gas plus 3s2 gas giving 2NS3 gas. Okay. So here the forward reaction is exothermic. The forward reaction is exothermic. That is, it gives heat out. Okay, delta H is negative. The reverse reaction is endothermic. Reverse reaction is endothermic. Okay, so in general, okay, any temperature increase will favor the endothermic reaction because which requires heat. Endothermic means it absorbs heat, so it requires heat. Therefore, any temperature increase will favor the endothermic reaction. Okay, so then exothermic reaction, any temperature decrease will favor the exothermic reaction. Therefore, by changing temperature also, you can manipulate this system. Okay, the forward reaction is exothermic. So here the production of ammonia will be favored by the reduction of temperature. Okay, so the reverse will be favored by the increase in temperature. Right? Okay, this is how the temperature change affects. The temperature will shift the equilibrium so that even the constant will get changed. Okay, the temperature is the one parameter which will change the equilibrium constant itself. Okay, so this is the general change about the temperature. So any temperature increase will favor the endothermic reaction, temperature decrease will favor the exothermic reaction. But even though the temperature decrease favors ammonia production, at very low temperature, okay, the rate of reaction is very slow. So therefore, a moderate temperature is maintained for the production of ammonia, right? Okay, so at very low temperature, okay, the reaction rate is very less. That is why we maintain a moderate temperature for the production of ammonia. So generally, the temperature increase will favor the endothermic reaction and decrease will favor the exothermic process. Okay. Then effect of addition of inert gas does not change the equilibrium much, but does not change the concentration or the partial pressure much. Therefore, if you add an inert gas which is not reacting with the gases in the system, okay, then it does not affect the equilibrium constant. It does not affect the equilibrium because the concentrations are the partial pressures are not changed. Then last, the effect of catalyst. Okay, the catalyst is favoring both the forward reaction and the reverse reaction. Okay, the catalyst is used to attain equilibrium faster. Okay, it does not change the equilibrium. It is helping us to attain the equilibrium faster. Okay, so the catalyst favors both the forward reaction and the reverse reaction. Okay, therefore the use of the catalyst is used to enhance the speed of the reaction. Basically, it does not change the equilibrium. Right? Okay, effect of catalyst. Okay, therefore, even in the production of ammonia, we are using catalyst. Similarly, there's another important process called contact process. SO2 gas, okay, plus okay, O2 gas giving 2SO3 gas. Okay, so for this reaction also use a catalyst which is V2O5. Okay, right? So for contact process we are using catalyst V2O5 or platinum. Okay, so the role of catalyst in equilibrium systems is to enhance the speed of the reaction. Okay, the equilibrium state is attained faster. For that only we are using catalyst, but again does not affect the equilibrium constant. Okay, it does not affect the equilibrium state. Okay, so this is how the different conditions, by manipulating the conditions, we can increase the product yield. Okay, in the equilibrium systems, because the reactions will never go to completion in the equilibrium system. Therefore, the yield will be low. Okay, so by removing the products, by increasing the concentration of reactants, okay, or by adjusting the pressure and volume, okay, we can increase or by changing the temperature, we can increase the yield of the products. Okay, so this is called Haber process, manufacture of ammonia. Okay, the temperature is around 500 degrees centigrade. Okay, and 200 atmospheric pressure we are using. Okay, even though the low temperature will favor the production of ammonia, to increase the speed of the reaction, we have to use a moderate temperature. Okay, stop பண்ணிக்கலாம் இது வேணாம். So final statement. Fine. Okay, right. So with this we complete. Okay. So with this we complete the equilibrium part of this equation. Okay, the ionic equilibrium. Okay, we will deal separately in another video. You can watch this space for chemistry videos. Okay, related to your NCERT topics. Okay, or NEET related topics. Okay, you can watch this space for more chemistry video. Okay, this is Anthony Raj signing off from NEET Gateway. Thank you.